In this first part, we're going to look at how digital cameras work. As you can probably remember from your school days, visible light is in a spectrum of indigo through to red. So that in waveform is 750 nanometers to 380 nanometers. But with an astronomy camera, you can actually record light in the ultraviolet, which goes up to 1000 nanometers. A colour camera uses a filter of groups of 4 red, blue and 2 green in what's called a Bayer pattern. A photon of blue light will pass through only the blue filter and hit the corresponding pixel on the sensor array. Each pixel has a corresponding well where the electrons are stored. When the image is complete, the number of electrons is measured through an analog to digital converter. The ISO or gain setting has the effect of amplifying the signal. The converted digital signal is then stored into memory, which can be exported out to a computer. Instead of using a one-shot colour camera, a monochrome camera can be used by taking 4 different images, each with a filter for red, green and blue, and one of luminous covering the whole spectrum. Of course, this will take 4 times longer, but it will give you 4 times more definition of the image. The light from deep space nebula is caused by the ionization of mainly 3 gases of sodium, hydrogen and oxygen. So with a monochrome camera, these narrow bandwidths can be isolated using narrowband filters, which will eliminate any light pollution from other sources. The Hubble Deep Space Telescope uses the same process and interprets these 3 bands as either being red, green and blue, and produces images in what's called the Hubble palette. We'll take a look at the specifications of the camera that I use for deep space objects. The first is the sensor type. So my Canon 1000D is a CMOS sensor as opposed to CCD. The sensor size is 22 by nearly 15 millimeters, which is APS, which stands for Advanced Photo System, and the C stands for Classic. This is Canon's version of the classic size. They do vary depending on the manufacturer. The full frame size is 36 by 24 millimeters, so anything less than that is regarded as being cropped. Is sometimes expressed as a fraction of the full frame. Just like a TV, the number of pixels will have a bearing on the quality of the image, but the number of pixels also has an impact on the size of the file that will be exported. Similarly, the size of the pixel will impact on the sharpness of any image captured, and the size of the pixel it's a square pixel, so it's 5.71 micrometers by 5.71. So let's add that information to our definition. So a sensor has its own frame size, pixel count, pixel size and readnoid characteristics. CMOS sensors generally produce more noise, but requires significantly less power than a CCD sensor. The crop factor is a comparison to a full frame of 36 by 24 millimeters. And the APC Classic is a common crop size of about 25 by 17 depending on the manufacturer. When buying a camera lens or OTA, you should make sure that it's matched to the camera sensor crop size. And pixels in a camera refers to the individual photoelectric cell that detects photons. Its size is usually measured in micrometers, i.e. 5.7 by 5.7 micrometers. The number of pixels in a sensor array is usually rounded to the nearest thousand, i.e. 10 megapixels. So my Canon camera is quite old. The ISO range for it is 100 to 1600, but in more modern cameras you'll get that range a lot higher, maybe 100 to 102,000. ISO is a setting in DSLRs, but in modern astronomy cameras the equivalent is called gain. ISO or gain, in very simple terms, is the amount of amplification applied to the ADC, having the effect that as increased, the well depth is decreased. ISO steps double or halve, i.e. 100, 200, 400, 800, 1600, but gain steps are logarithmic. Too low and your image may be underexposed, too high and it may be overexposed or blown out. The bit depth of a camera is how many tones of colour it can record for each pixel. So a bit depth of 1 bit, pixel would only be either black or white. And a bit depth of 2 bits, it would be black, dark grey, light grey, and then white. So a 12-bit camera, such as this, gives you over 4,000 different tones of colour. And a 16-bit camera would give you over 65,000 different tones of colour. This causes a problem when you come to display the image because you're using a 16-bit container to display only 12 bits of data. So what we have to do is stretch the data so that it actually fills in the whole 16 bits. So here's an example of a subframe that I've taken. It's in its linear state, which means that it hasn't been stretched yet. But as soon as we stretch it, you'll see the difference, that it brings out more detail. Bodes and the cigar galaxies are beginning to appear. The speed that I can export images out of the camera into the computer is governed by the USB standard. So with this camera it's USB 2, which is equivalent to 480 megabits per second. 400 megabits is about 60 megabytes per second, so a 15 megabyte file would take about a quarter of a second. For planetary work, however, I use a much faster camera which has a USB 3 output, which is 625 megabytes per second, so I can export about 40 files per second, which is required when taking shots of the moon or planets. So finally, noise. And the only thing I can find about my camera is it's specified as having low noise. But normally for a dedicated astronomy camera, you will find a graph of the amount of noise you can expect depending on the gain setting of the camera. But what is noise? I guess the best way of describing noise is to show you an example. I'm going to use some software called Graspert, which is designed to reduce noise. So here's an image I've recently taken. When you zoom in, you can see that there's what's called salt and pepper. It's little dots of different colours. When I denoise it, you can see the effect. It's greatly reduced the noise. A major cause of noise is either the ISO or gain setting. I'll example this by a quick video I've taken using my dedicated planetary camera with the fisheye lens that comes with it for testing purposes. I'll first set the gain to 0 and the exposure rate to match it. And as we zoom in, you can see there isn't a lot of noise. But I'll now increase the gain to its maximum and blow out the picture. So I need to reduce the exposure time. And now when we zoom in, I'm sure you can see the noise. In this video we can add some more definitions. So the bit depth of a camera is the maximum number of bits that can be counted per pixel. A 12-bit camera can store about 4,000, while a 16-bit camera will store over 65,000. The full well depth is the maximum number of electrons that can be stored in each well at the lowest gain setting. It's usually measured in thousands, i.e. 50,000 electrons. Signal to noise. Signal is good, noise is bad. Noise is mostly created by the electronics and how close the pixels are together, the sensor's temperature, the type of sensor, and CMOS creates more noise than a CCD, the ISO or gain setting, and the length of exposure. The signal to noise ratio is a quality measurement of the camera. And finally, the quantum efficiency is how good a sensor is at detecting photons. If a sensor detects 75 photons out of 100, it would have an efficiency of 75%. CCDs generally are more efficient than CMOS. In the next video, we'll look at different sorts of cameras and how they can be used.